In a spreadsheet, we can use a random number generator to simulate the fates of individuals. So we can simulate whether an individual dies or whether it survives. So we can ask this random number generator to select a number randomly between 0 and 1. And if it selects a number that's between 0 and our survival rate, which is 0.6, we'll call that individual a survivor. If it selects a number now between 0.6 and 1, we'll call that an animal, an individual that dies. Now we can do the same for births, right? We have a 0.4 birth rate. We could select a random number. If it fell between 0 and 0.4, then we would call the individual of concern one that gave birth. And if we selected a number that was between 0.4 and 1, then we would call that individual a non-producer, or an individual that does not produce an offspring. So we might end up with a spreadsheet that looks something like this. So we have our survival rate up here at the top. Our survival rate, of course, is the opposite of our death rate. So if our death rate is 0.4, we would expect our survival rate to be 1 minus 0.4, which is 0.6. And we have our birth rate here. Our birth rate is 0.4. And so what we've done is we've created a column here of individuals, and we have 10 individuals. We've got all 10 in our panda population. And we've asked the computer to draw a random value between 0 and 1. And if that random value falls between 0 and 0.6, which is our survival rate up here, we will call that individual a survivor, and we'll give it the value 1. So the first random number selected is 0.38, which you can see here. So in that case, we have a 1. We've got a survivor. In this next case, individual number 2, we drew a number that was 0.9, a random number. So in this case, this individual unfortunately would die, so we would give it a 0 value. It wouldn't survive until the next year. So we do that again for all of our individuals in our population. So then we deal with the birth side of things. That's the survival side of things. Let's deal with the birth side of things. In this case, we do the same process. We estimate a random number. We ask the computer to draw a random number between 0 and 1. And if that number falls between 0 and 0.4, our birth rate, we'll call that individual reproducing, and we'll give it a 1. So that's an individual, number 1 here, that produced an offspring. In this second case here, we've drawn a number that's between 0.4 and 1. So in that case, we would say that's a non-reproducer, and we would give it a 0 value here. So what do you notice about the results? If you look at the results here, we had a total of 5 survivors, and we had 2 that were born. Think back to how we worked with population, survival rate, and birth rate on the population as a whole. When we applied those numbers to the population as a whole, we found that that population of 10 pandas, it didn't change, right? So we started out with a population of 10. We had a total of 6 survivors and a total of 4 that were born. So that was from the previous example. And so that would give us a population of 10, one time step away. So at the population level, when we apply these average measures, that's what we end up getting. And that's what we'd expect. But what happened here? We didn't get that many. Instead of 6 survivors, we had 5 survivors. And instead of 4 being born, we actually had 2 being born. So here, our total population ended up being 7, not 10 as we expected. Why is there this disparity? There are no other factors here affecting this population except for randomness. It's this random variation that's produced these numbers. The disparity between what we'd expect and what we actually observed is due to this random effect, and that's the realm of demographic stochasticity. In this case, we're dealing with a small population. But how does demographic stochasticity affect perhaps a larger population? Well, we can carry out the same procedure we just went through, but do it now for two populations and make some comparisons. So we can use that random number generator to simulate the fate of two different populations and estimate the population size in 1 year's time or one time step away for each one of those populations. And not only that, we may do it 100 times. We might simulate that process 100 times and summarize the results. So in this case, let's consider a population of 10 pandas and a population that's larger, let's say 25 pandas. Run through this procedure, simulate 100 times for each, and see what the results look like. So here's that graph. Here's a graph of the results. We've got number of survivors down here on the x-axis and number of trials here on the y-axis. And again, we're dealing with two populations. A small population that consists of 10 individuals and a larger population that consists of 25 individuals. So again, we have for this population a survival rate of 0.6, and we're applying that survival rate to each individual in the population using this random process that we just went through. So we apply that rate to each individual, and then we summarize how that population behaved afterwards. So if we started with a certain number of individuals and we carry out this process, how many individuals at the end of it do we have, or those that survive into the next year? So we've done that for our population of 10, and we've done that for our population of 25, and we not only did it once, we did it 100 times. So we carried out this process 100 times, and that's what this graph summarizes. So you have the number of trials again on our y-axis and number of survivors on the x-axis. So for our small population, you can see here we had, it looks like just 1 or 2 trials that resulted in actually 10 individuals surviving to the next year. Now, if you remember back to our earlier exercise in which we applied this survival rate to the population at the whole or at face value, we estimated in our small population that we would have 6 survivors, right? We would expect to have 6 individuals that would survive. So that's 60% of 10. We would have 6 out of 10 surviving from one time period to the next. Let's say for our pandas over 1 year. For our larger population here, 60% of 25 would be 15. So we would expect to have 15 individuals survive out of the 25. But if you look at these results here, what we find is that we had only 27 trials, 27 now resulting in our expected value for our small population. And we actually had 17 trials that resulted in, here, our expected value. If you look closely now, you can see that actually there's a huge amount of variation in terms of the numbers that we received. Quite a bit. So there was actually a fair amount of difference between what we got versus what we expected. And this deviation here, this is all deviation away from what we expected, is a key point. And that is, again, that the amount of this deviation gives us an indication as to the effect or the magnitude of stochasticity on population size. So how do we measure this deviation? Well, we oftentimes estimate some variance measure, some measure of the variability of our data. And a common one is standard deviation, which you might remember from basic statistics. Terry will walk you through how to calculate a standard deviation, but essentially what it is a measure of the spread of our data around an average value, around a mean. And it's technically the square root, if you can envision this, of the sum of each data point minus the mean squared over our population minus 1, or our total number of data points. It's a little complicated, and Terry will walk you through that shortly. So if we estimate standard deviation for our small population now, our population of 10 pandas, we end up with a value that turns out to be 1.6. So that's giving us a measure of the spread of data around our mean. For our larger population now of 25 pandas here, our standard deviation is 2.3. So we have 1.6 for the small and 2.3 for the large. How do we interpret that number? What do those two numbers mean if we were to compare them? It seems like because 2.3 is a much higher number than 1.6, and because these values represent some measure of variance, one might assume that this larger number equates to more variability around the mean. So there's more scatter, more dispersion of data around our mean for the larger population. Is that in fact the case? Let's have a look at this graph again. So what do you notice about the distribution of data here? Have a look at the distribution. Remember, we've got two populations, one of 10 and one of 25. If you consider our population of 10, how many possible outcomes could we have obtained from our trials? We could have obtained 11 possible outcomes, so that's 0 all the way up to 10. So there are 11 total possible outcomes. How about now for our population of 25? How many possible outcomes could we have obtained? Well, they range from 0, this time now, all the way up to 25. So we have 26 possible outcomes that could have occurred. So let's look at our smaller population. If we consider our smaller population here in the data that we have, if you look closely, the values that we obtained covered or included nearly every value in our possible spread of outcomes. So we had almost every single possible outcome occurring, including some instances here in which we only had one individual surviving, indicating what? That the population went extinct. So there's actually a lot of variability here. Let's compare that now to the spread of data of our larger population. So the spread of data here actually cover only about half or so of the possible outcomes that we could have obtained. So in other words, there is really less dispersion of data across possible outcomes than the smaller population. But remember, the smaller population had a small relative standard deviation compared to the large population, which gave us the illusion that the large population now was more variable. But just by looking at the spread of data here, we see that the opposite seems to be true. So one thing to point out is that a general property of data is that the mean and standard deviation tend to change together, and that's probably why we see this illusion of sorts. In other words, as the mean gets smaller, the standard deviation kind of changes relative to that and also becomes smaller, and as a mean becomes larger, that standard deviation can also become a bit larger as well. So how do we deal with that issue? How do we correct for that in some ways? How are we able to make comparisons between two populations, comparisons between their variability? There is a solution here, and that is to calculate something called the coefficient of variation. And we sometimes give that the abbreviation CV. So coefficient of variation is simply a means of standardizing the amount of variability in a data set. So if we standardize that amount of variation that we see in one data set and do it also for another data set, we can then make comparisons between the variability among them without this issue that we faced with standard deviation. So the coefficient of variation is simply calculated as the standard deviation divided by the mean of our data. That's it. So the standard deviation, for example, of our first population, the small one, was 1.6. and the mean of our data, I believe, was about 6. So that will give us a new value, a coefficient of variation value. If we do it for the second population, we can directly compare the two of them. In the case of our pandas, our small population now has a coefficient of variation of 0.27. Our larger population now, our 25 population, has a CV, or coefficient of variation, of 0.15, considerably smaller. Now that we've standardized our variation, we can now directly compare these two populations. And what you notice now is the tables have turned, and the smaller population has a lot more variability around its mean. There's more scatter to the data. There's a more pronounced effect of that demographic stochasticity, that randomness on the small population. So this coefficient of variation is very handy in allowing us to make those comparisons. What sort of implications are there then based on these results? Well, they show in some respects that demographic stochasticity, this random variation, this random average variation in survivorship and in reproduction, can have a more magnified or pronounced effect when populations become really small. So as managers, let's say we are perhaps tasked with trying to ensure a viable population of Przewalski horses, one of my favorites. This was a species that went extinct in the wild and was reintroduced, and there is a small wild population existing in Mongolia. So in this case, we have a small population. We might do all sorts of things to control the population. We might do a great job at removing some of the immediate threats that humans might be causing, or various other effects that could jeopardize the population. But because the population's small, we still need to recognize that these random processes can still have pretty significant consequences for these small populations. So we need to, in many ways, just consider that as a potential force that we need to incorporate into our management. So I'm going to pass you over to my colleague Terry. She'll build a spreadsheet that will walk you through much of what we've covered, and I think by the end of it you'll have a much greater sense for the mechanics of how demographic stochasticity works.